In this video, we're going to review the graphical approach to limit, talk about piecewise functions and limits, and also deal with limits and infinity. First of all, the question, where does the limit not exist, we're going to come back to. We're going to start by answering the rest of these, like what is f of negative 1? This is just saying what's the function's value at negative 1. Well, at negative 1, the function's value is defined as negative 1. Next, what's the function's value at 1? At 1, the function's value is 2. And finally, f of 5 is just again saying what's the function's value at 5. The function's value is 3. Easy enough. Now we start dealing with limits. The limit as x approaches negative 1. Well, you'll see that it's approaching negative 1 from both the negative side and from the positive side. It's approaching a y value of 0. So that's the limit. It doesn't matter that that's not the function's value. Remember, a limit says what are you approaching from either side. So the fact that the function's value is negative 1 is not important to finding the limit. The limit's 0. Next, the limit as x approaches 1 from the negative side. So as we approach positive 1 from the negative side, we're approaching a y value of 2. Next, we're approaching 1 from the positive side. So approaching 1 from the positive side, we're approaching a y value of 4. So you'll notice that actually at 1, since it's approaching 2 from the negative side and 4 from the positive side, the limit at 1 does not exist. So we could go back up here and say, well, where does the limit not exist? One spot is x equals 1. Next, 5 from the negative side. So we go to 5 from the negative side. We're coming over here. We're approaching a y value of 3. And finally, approaching 5 from the positive side. We're approaching a y value of 1. And again, you'll see that this is a spot where the limits from the left and right, from the negative and positive side, are not the same. That means at 5, the limit does not exist. So I could add that up here. X equals 5 is the other spot where the limit does not exist. Now, in a situation like this where you're given the equation but not the graph, you could certainly draw the graph. You could say, well, it's x plus 2, so it looks like that with a closed circle there. It's x squared, so open circle and closed circle here. You could certainly draw that piecewise function and get the answers that way, but I'm going to try it without it. If I'm approaching 0 from the positive side, that means I'm looking for the function that's bigger than 0. Well, this is the function that's immediately bigger than 0, and if I plug in 0 to this, I get 0. Next, from the negative side, approaching 0 from the negative side, well, if I'm going to go to the equation that's below 0, so this one, and I'm going to plug in 0 because we're approaching 2. Now again, you can look at the graph and say, okay, so from the negative side you're approaching 2, from the positive side you're approaching 0, and you see the graph may make that easier, but we didn't really need the graph to answer that question. Finally, the limit as x approaches 0, well, this is where we look and we say, well, from the positive side it was 0, from the negative side it was 2. So the limit there does not exist. Because for the limit to exist, they would have to be the same, the positive side and the negative side. Next, approaching 2 from the negative side. So let's go to the one that's below 2. It'll be this one because it goes from 0 to 2. So 2 squared is 4. Next, we're going to 2 from the positive side, so we go to the one that's bigger than 2, and we plug in 2. Negative 3 times 2 is negative 6, plus 10 is 4. So what must happen here, and I never finished the picture, but it must do something like that, because they actually do connect. So the limit there is 4, because it's the limit is the same from both the negative and positive side. Again, you could draw the picture and do that, but it's probably just as easy not to, because all you need to prove is that, for example, at 0, if we plug 0 into this equation, x plus 2, if we plug 0 into this equation, x squared, the fact that they're not the same, we know the limit does not exist. You may want to graph these as we go along to verify the limits, but I'm just going to kind of go through them quickly without a graph. The limit as x approaches 0 of 1 over x, if you think about what that function looks like, I could draw a quick sketch. It looks something like that. The limit at 0 does not exist because it's approaching negative infinity on one side and positive infinity on the other. The limit as x approaches infinity means as you go out towards infinity, what happens? Well, it actually is going to hover right at 0. And you'd know that from the equation because 1 divided by a really, really big number is approaching 0. It's not 0, but that's what it's approaching. And it will be the same going to negative infinity. The only difference is, of course, one direction it's approaching 0 from the positive side, the other direction it's approaching 0 from the negative side. The cosine of 1 over x is worth graphing. We did that in class. It goes along like this and then oscillates and then goes back off. It's an oscillating function at 0, and therefore the limit does not exist. The limit as you go towards infinity, well, it actually ends up just being 1 in both directions. And the way you'd maybe know that from the equation is if you plugged in large numbers, this 1 over x, we already said, gets close to 0. We said that up here. Well, the cosine of 0 is 1. And is 1 here as well. So if we look at 1 over x is approaching 0, and the cosine of 0 is 1, so we can calculate the limit that way. The sine of 2x over x, we talked about this one in class, the fact that we know that if the coefficients were the same, that the limit would be 1, but they're not. So that means we multiply top and bottom by 2. And then what's inside the bracket? The limit is 1, so 2 times 1, this limit is 2. Now, let me get rid of this little work here. The limit as x goes to infinity. Well, you got to remember that sine is bounded between 1 and negative 1. It won't get bigger than that. And this will continue to grow without bounds. So what we do is we have something small divided by something really big. Well, that's approaching 0. And the same thing is true going the negative way. We'd just be dividing by a negative big, but they would both be approaching 0. For this last one, I would urge you to graph it because what you're going to see is an asymptote at 0, so the limit does not exist. You could look at that algebraically, but I think graphically is the best way to do it. As you go towards infinity, I want to talk about this one. You plug in large values, we get 10 to a negative big number. Well, this is approaching 0, because 10 to a negative big gets really small, and the bottom gets really big. Small divided by big approaches 0. Now, if you plug in negative big numbers, 10 to a negative big becomes 10 to a big. So the top gets very big. The bottom gets big, but an exponential is bigger. So what you end up with, as silly as it sounds, is you end up with bigger over, I guess in this case, a negative big. So the limit is negative infinity. And again, please graph that and take a look. Real quick, talking about end behavior, and this will be a really quick discussion. the end behavior, you all know what a cubic function looks like. It looks something like this. So if I were to ask you, what's the limit as x goes to infinity? It is positive infinity. If I were to ask you what the limit is as x goes to negative infinity, you would say negative infinity. Next to the fourth, we hopefully know what that looks like. This is the one that kind of looks like a W, like that. So if I asked you what's the limit as x goes to negative infinity, it would be positive infinity. And if I were to ask you what the limit is as x goes to positive infinity, it would be positive infinity. So we can use our knowledge of a function to do those limits very easily. And the same with this, because what is end behavior but describing the horizontal asymptotes? If you think about what a horizontal asymptote does, if I just draw a quick sketch and put a horizontal asymptote in, the function probably looks something like that. And that describes its end behavior. So you remember your rules, I hope, from pre-calc. If the highest power is in the denominator, which in this first example it is, the highest power is in the denominator, okay, the limit is 0 in both directions. Because that asymptote, and again, this is just a general sketch. It's not either one of these functions. This is just a sketch. But that horizontal asymptote is the limit in both directions. Okay? So in our case, highest power on the bottom in the denominator, the limit is always 0. Next rule, if you have the same power on the top and bottom, if you recall, you just make a fraction out of those coefficients, and again, it's the same in both directions. It's just 1/2. Okay, you have those three situations. High power in the denominator, it's always, the asymptote was always y equals 0. In the numerator, there is none. And same power, you got to do what we did up here, make a fraction out of the coefficients. And the nice thing is those asymptotes are the same as the limits. So one more time, if the highest power is in the denominator, like it was here, the limit is 0. If they had the same power, you just make a fraction out of those coefficients of the biggest power. And if the numerator had the highest power, then there is no limit.